So we're going to turn now to our next session, which is Computable Biomedical Knowledge, Revolutionizing Biomedical Research. We have two outstanding speakers to address this topic for us. Grace Peng, whom I will introduce in more detail in a moment, from the National Institute of Biomedical Imaging and Bioinformatics of the NIH, and Herbert Soro of the University of Washington. The way this panel is going to work, Grace will speak first, and we will have a short Q&A session immediately following Grace's presentation. Following that first presentation, then Herbert Soro will speak, and we should have at the end of Herbert's presentation time not only for questions directly put to Herbert, but for additional questions put to Grace as well. So let me, without further ado, introduce Grace Peng, our first speaker. Grace is the director of the mathematical modeling, simulation, and analysis work at the National Institute of Biomedical Imaging and Bioengineering, NIBIB, within the NIH. In this capacity, she has programmatic oversight over the extramural activities in these areas. Dr. Peng, Grace, received her bachelor's degree in electrical engineering from the University of Illinois at Urbana, and a master's and PhD degree in biomedical engineering from Northwestern University. She performed postdoctoral and faculty research in the Department of Neurology at Johns Hopkins University, and in 2000 became the Clare Booth Luce Professor of Biomedical Engineering at the Catholic University of America. Since 2002, Dr. Peng has been a program director in the NIBIB, overseeing various programs, promoting the development of mathematical and statistical modeling and analysis methods, medical simulation tools, and next-generation engineering systems for rehabilitation, robotics, neuroengineering, and surgical systems. In 2003, Dr. Peng led the creation of the Interagency Modeling and Analysis Group, abbreviated IMAG. And since 2004, IMAG has supported funding activities targeted to multi-scale modeling of biomedical, biological, and behavioral systems. Since 2006, IMAG has facilitated the activities of the Multi-Scale Modeling Consortium of Investigators. Dr. Peng is committed to promoting the development and use of intelligent tools and reusable models to accelerate biomedical research and translate scientific knowledge to the clinic and community. And this obviously situates her extremely well to speak to the intersection of MCBK and the future of scientific research. Grace, we are absolutely thrilled to have you with us today. Welcome, and we very much look forward to your presentation.
Thank you, Chuck, and the MCBK organizers. I'm very happy to be here, and thank you for inviting me. I'm pleased to talk to you today. MCBK, I believe the revolution is indeed happening. So first of all, I would like to congratulate the MCBK for creating a manifesto and a vision that I believe really truly resonates among multiple biomedical communities. And I will use this talk to give you examples on how this vision is already being realized. So if we look at the very first vision statement, it says mobilizing biomedical knowledge can support action toward improving human health. This should be done using computable formats that can be shared and integrated into health information systems and applications. This means we need to encourage communities to put knowledge in computable formats. So we need to first convince the communities to put knowledge in computable formats. And the first example I'm going to show is a community that has been convinced. And this is an initiative that I'm working with at the NIH. It's called the HEAL Initiative, helping to end addiction long-term. And in particular, I'm involved in the Back Pain Consortium, otherwise known as BACPAC. So BACPAC's goal is to reduce opioid abuse by addressing long-term or chronic low back pain. But in order to treat the chronic pain associated for each individual, the consortium realizes that we need to understand the mechanisms behind lower back pain. And furthermore, they have come to understand that in order to really understand the mechanisms, we need computer models. And so this is a really huge step forward. And so the theoretical models working group within BACPAC, looks at lower back pain through these different factors. And so when you think about back pain, there's all these factors that are involved, and they're looking at the biophysical, the comorbidities, the genetic factors, psychological factors, social factors, all contributing to the pain experience, creating the low back pain disability. So this theoretical models working group then took on the challenge of sort of looking at it from a systems point of view and putting all these inputs together in a diagram that sort of talks about the inputs and the outputs and how these different dynamics can contribute to lower back pain, including the psychological, the societal, the systemic, the familial, in addition to the biomechanical, the musculoskeletal, and all those essential pain processing. And underneath these diagrams, they have further created these boxes of the different components that contribute to this very complex system. And so this is the first step in looking at a computable biomedical knowledge environment, is to really create these computable knowledge components. And so they've really moved from this very simple, straightforward input-output system to a more complex system that depicts how we can explain not only the anatomical components, but the distributed processes and the emergent phenomenon that could happen with each individual and their own pain experience. Furthermore, I'm really excited that this consortium has embraced modeling to the point that they are saying in their research agenda for the entire consortium that the #1 goal is to develop this theoretical model, instantiate it with math and statistics and the dynamics for computing, and to develop the testable hypotheses to drive the following experiments and the clinical trials that need to be conducted. So I really believe this is a good step forward and truly using model-driven, the model-driven philosophy to drive future experimentation. So if you look at the next vision of the backpack, the MCBK manifesto, the idea is to efficiently and equitably serving the learning and knowledge needs of all participants as well as the public good. This will work significantly to reduce health disparities. So my next set of examples is the issue about serving disparate communities equitably, and the issue of medical errors. So this is data from 1996, which then led to the National Academy's report on To Err is Human, and how deaths from medical errors are the leading cause of death over motor vehicles, and including airplane aviation deaths, which is actually in the smallest category. Now move ahead, 17 years later, the number has doubled, more than doubled to 250,000 deaths annually. And this is an underestimate based on the authors of this publication. Medical errors now is considered the third leading cause of death by the CDC before COVID. After COVID, now medical errors is number 4, COVID is number 3. But it's one of the leading causes of death after heart disease and cancer. And so this is a condition that we need to address. And how do we address that? And so in 2016, my institute, NIBIB, along with NIDDK, the Digestive and Diseases and Kidney Disorders Institute, we had workshops and created reports on how to address medical errors and increase patient safety through medical simulators. And so we ended up creating this funding opportunity that's currently out on the streets for promoting medical simulator development for practicing patient care providers. Those providers in the field currently working on our own medical care right now, and developing projects for assessing skill acquisition, outcomes assessment, and technology development. And so this is really a step forward to try to really bring in computable knowledge to medical simulation. And the algorithms that we really want to try to support are physics-based as well as artificial intelligence-based algorithms that really present some challenges in simulating and emulating the procedures and the processes that happen every day in our hospitals and clinics. And so this is truly a way to incorporate computable knowledge into the simulator environment. So if you go back to 1960, and JCR Licklider said that in not too many years, human brains and computing machines will be coupled together very tightly, and the resulting partnership will think as no human brain has ever thought. And so that was a very futuristic statement in 1960, and now we have the Google car and the Tesla truck. And if you have a chance to look at this YouTube video from Oakley Radar Pace, these are athletic glasses used by athletes to get virtual coaching, in which this voice whispers in the athlete's ear while they're climbing mountains and running marathons and pushing the athlete to move faster based on their own physiological parameters and their goals. This is a virtual coach, and that's what we're actually trying to do in terms of medical simulation, is to create virtual coaches for reducing medical errors and increasing patient safety. Moving on to the next vision, ensuring that knowledge properly reflects the best and most current evidence in science. This will ensure that knowledge can be trusted for use to improve health and health care. So in other words, we need trusted knowledge. So as Chuck mentioned, I coordinate the Interagency Modeling and Analysis Group, otherwise called IMAG. We are now over 100 program directors from multiple government agencies in the United States, funding activities to promote modeling and analysis of biomedical, biological, and behavioral systems. And so modeling supports these analysis programs, and we have been supporting multi-scale modeling since 2004 and the creation of the Multi-Scale Modeling Consortium, where we understand that the components of the human body go from the atomic to molecular to cellular to tissue to organ to whole system and population levels. And all of these components create a mechanistic view of how our body and physiology works. And so in this consortium, the investigators have broken up into multiple working groups and task forces. And so this is open to all. If you're interested, you're welcome to contact me to join any of these working groups and our consortium. But we talk about methodologies that cross scales, deal with uncertainty, we address sparse data, we talk about basic science application and biomechanics and neuroscience and materials. And we also have a clinical translation task force. And I'll focus on the task force on dissemination, which our next speaker, Dr. Herbert Sarro, is also involved in. This particular task force has a committee on credible practice of modeling and simulation in healthcare, as well as a model and data sharing working group in public and dissemination and education. Now, these working groups, as you can see, can very much affect the public good and improve the trustworthiness of the computable knowledge. So I'll focus on the one committee on credible practice of modeling and simulation in healthcare. They have been adopting many of the validation principles that NASA had to implement after the Challenger shuttle tragedy. And through that adoption of the validation principles for models, they created these 10 simple rules for credible practice of modeling. Now, these 10 simple rules are actually quite simple if you look at it, but they're actually not so simple when you're trying to implement it. So the number one rule is to define the context of the model that you're developing clearly. Number two, use appropriate data. Number three, evaluate within the context. Number four, list limitations explicitly. Again, using version control, documenting. So these 10 simple rules pretty much walk people through the model development process, and it should be used as a practice to continuously assess how well you're doing in each of these. We've actually developed now an online tool, a form on our wiki site for the Multi-Scale Modeling Consortium to use this tool in all the modeling projects to assess credibility and conformance. And so in actuality, in these COVID times, we have been approached by the CDC to try to assess the credibility of the COVID models that are currently being used during this pandemic. And so again, the consortium, the Committee on Credible Practice, along with NASA, within IMAG and CDC, NIH, and DARPA are all joined forces now to implement the 10 simple rules for credible practice of modeling for these COVID models. And the upper right-hand corner shows the wiki page with the conformance rubric. And so DARPA is actually helping us try to automate this process of assessing the 10 simple rules. But this is just an example of how our community has come together to realize the need for credible models. And now with COVID, the need to really address it so that the community can better understand the credibility of these COVID models. Moving on to the last vision, achieving this through an evolution of an open, computable biomedical knowledge ecosystem dedicated to achieving the FAIR principles, making CBK findable and accessible and interoperable and reusable. So that's really important. One thing that Herbert Sauer and I, the next speaker, did was in 2015 and 16, we were involved in the IEEE Engineering and Medicine and Biology Society special interest group for physiological models. And we had a special issue on basically experimenting how we can make models reproducible through publications. And we brought together multiple editors from multiple journals, and we solicited this special issue in which we used the special issue as an exercise to understand the process of making the models reproducible. The authors contributed models to execute by the reviewers, and the reviewers simulated the models and provided feedback back to the authors. And the process was documented in this special issue. It was a very interesting and enlightening process that really opened our eyes to a lot of the hardships involved in making models reproducible, but making a better product at the end. And so Herbert will probably talk to you about his center that he created in 2018 for the producing reproducible models and the tools that he's developing to allow the community to produce reproducible models. So this is in order to find where we live, you can go on the browser and search IMAG Wiki, IMAG space wiki, and you'll find our consortium activities. Finally, you heard Dr. Brennan mention the ABLE initiative that's just brand newly approved by the NIH Councils of Councils, and the importance of this, the NIH Artificial Intelligence Working Group recommendations to include not only the data, the people, and the ethics involved in creating the next generation machine learning friendly data sets, but also the tools that are important to make these data sets readable and understandable by future machine learning models. Finally, I will end this talk with this concept in which in October 2019, not so far away ago, the Multi-Scale Modeling Consortium, along with IMAG, had a meeting on integrating machine learning with multi-scale modeling, and we focused on creating digital twins to address health and disease. This image was provided by Medtronic that describes the integration between that needs to occur between the physical sciences and the anatomy and the physiology and the digital threads of electronic health records, sensors, and the Internet of Things, data science, which includes machine learning, statistical analysis, and big data analytics, to create this digital twin of us, a digital twin where not only can we try to optimize our health and predict adverse events, but to plan interventions, extend the quality of life, and to extend life in general. So I do believe the vision of the MCBK can help us in this direction and create this dream. So this ends my talk, and I'm open to hearing any questions you might have. Thank you.
Thank you so much, Grace. We have not received any questions to this moment. I was just checking my screen. The questions come in via email. So let me encourage folks to submit your questions, and we will put them to our panelists. So Grace, stick around, don't go anywhere, and we will engage back in a question and answer session as soon as Dr. Soro finishes his talk. So let me now introduce Dr. Herbert Soro, who is a professor at the University of Washington in the Department of Bioengineering in Seattle. His professional interests include modeling, control of cellular processes and model exchange standards, and reproducibility in biomedical research, so very relevant to MCBK. He is currently the director of the NIBIB Center on Reproducibility of Biomedical Modeling. Dr. Soro holds degrees from the UK in biochemistry and microbiology, computational biology, and systems biology. And as soon as you hear Dr. Soro speak, you will know that the UK is the United Kingdom and not the University of Kentucky. He was a founding member of the SBML development team at Caltech, has over 150 publications on topics ranging from metabolic control analysis, software standards, algorithms, reviews, synthetic biology, systems dynamics, and noise and reaction networks. He has published 7 textbooks, that's 7 textbooks on a variety of topics that include modeling, mathematics, and computer science. At the University of Washington, he teaches control theory and modeling biomedical processes. Herbert, we are just thrilled to have you here with us today, and we very much look forward to your presentation.
I'm very glad to be here today. I'm not a librarian, but I love libraries. So I come from a part of the world where it's sort of the middle of nowhere. If any of you have seen the TV show Hinterland, which is on Netflix, that's basically filmed where I come from. So it's the middle of nowhere. But we had a public library there, which I used to go to quite often. And it had a huge influence on me subsequently. And so I'm a big fan of libraries. So the question is, where do libraries go in the 21st century? I mean, I've seen changes at our own university in terms of library usage, and I'd like to see them stick around and not disappear. So I think we can all agree that models are more important than ever. There was an article in the New York Times in April that came out that discussed 5 of the COVID-19 models. And of course, the models have been used by policymakers to direct policy, and the reliability of those models is critical. The ability to reproduce those models is critical, and so on. So models are really important, and this is what I want to talk about: is computational models and where libraries can help us with those models. So I'm just waiting for the next slide. There was an interesting quote from 1995 by Buchheit and Donahoe, and they talked about publications as an advertisement. So they said an article, for example, about computational science in a scientific publication is not the scholarship itself, is merely advertising of the scholarship. And what the bit of insight they had was the actual scholarship is the complete set of instructions and data which generated the figures. And often that is missing. Often we see in publications that there's not enough information to generate the figures, or not enough instructions to do the computation again. And so if you look at publications today and how they're published, how models are published, I've got a list of 5 things in which you find how computational models are published. First of all, sometimes you find, I don't know what's happening to my slides, but anyway, never mind. Sometimes models are not supplied at all. The original code is not supplied at all with the paper. That's the worst case scenario. Sometimes you'll find the model described in an appendix, right, of the journal, for example, or in the preprint service, such as BioArchive. You might find the source code and the data on the author's website, or you might find the source code and data on a code repository such as SourceForge or GitHub. Or you might find the model stored in some kind of standard representation and stored in a dedicated model repository. So I think you can gather from this that 1 is the worst, and from my perspective, 5 is the best. All of them except for 5 pretty much have issues with them. Storing data and models on the author's website is a really bad idea because often the author's website disappears along with all the data and the code. So how widespread is this? So let me just give you an example. So this is an example of a published model. It was published in 2011. Right? This is something that happens currently. Now, somewhere in this text, there's an error. And of course, I'll ask you, can you spot the error? And of course, the answer is no. That's because it took a professional modeler about a week to uncover the error in this paper. So it's only one slight error, but it's embedded somewhere in the text. So if I zoom in on part of it, so the piece on the right you're seeing, that's a zoomed in section of the paper. And you'll notice that that section has equations in it. And those equations are actually the model. So the model is described as prose, or as well equations within the prose in the paper. So I wouldn't recommend that. But secondly, the main problem was that they got the units wrong on the diameter of the neuron. So this is a paper about modeling neurons. And of course, neurons are modeled like tubes. And they got the units wrong on the diameter of the neuron. And for that reason, the surface area was computed incorrectly and so on. And so the model couldn't be reproduced. And it took somebody a week to figure this out, to get the model working again. Now, this problem, you might think, must be quite rare, but actually it's really widespread. In fact, it's 2 independent studies showed that between 97 and 100% of models, at least in systems biology, have problems like this and are not reproducible. Here's a selection of things. These are actual papers. So you get problems like incomplete parameters, no parameters at all. The analysis wasn't described. The language that was used to describe the model or the software that was used is no longer available. 2 of these models I have here, one is actually quite a famous one in Science magazine, cannot be reproduced at all, no matter what you do. But what kind of mistakes do we find? Well, they're really mundane. These things like missing data, incorrect data, results published without the models, simulation environment no longer available, the wrong model supplied with the paper, all sorts of mundane errors like this. It causes huge problems though, because, so for one thing, I mean, it basically holds back scientific progress because people can't easily build on what was done before. What you'll find is that, well, first of all, models are scattered throughout the literature and on personal websites. As I said before, personal websites don't last forever and tend to disappear. The majority of models are inaccessible because they're published in an incomplete form. There's no quality control at the review stage. So when models get peer reviewed, reviewers don't either have the time or the expertise to try and get the model running. And it can take quite a long time to get the model running. Like the previous one, it took somebody a week to try to get running. So there's not much quality control at the reviewer stage. The code for the model is not always uploaded with the publication, and unfortunately editors don't enforce that. And so all these combined together are very costly in research and of course actual dollars. So this actually costs real money if you consider the time taken to try to recover this kind of information. So we realized this back like almost 20 years ago now. We had a similar problem in the systems biology field where people were publishing models, and we had a simple problem, which was that people were using different kinds of software and they couldn't exchange the models between the different software tools because each software tool used its own particular format, and you couldn't move one model from one tool to the other. And so a bunch of us got together and we decided to create this thing called the Systems Biology Markup Language, shortened SBML. And this is a common format that the community approved and is now widely used. So if you save your model in this format, you know that there are many, many other tools that can load this model and run the simulation. And what you will find is that simulation tools tend to come and go. So the simulation tools that we originally had in the 2000s are no longer available, but the SBML models that were developed with those tools are still available and can still be loaded by modern day tools. So the models persist, but the tools there's quite a bit of turnover in tools, which is why I always recommend trying to store things in some sort of common format that people can reuse later on in newer tools. Now, the biggest surprise, so when we developed this, we thought, well, this is all very nice. This will help everybody. What I didn't anticipate was there was a huge explosion in other things that then happened around this. Once we created this format, people started saying things, oh, I can use this for other things. I know, let's start building a repository of models. So now people started creating repository of models. They started thinking of all sorts of other applications like graphical standards, spatial models, and there's a whole range of things in this figure. You see there that people have been using SBML for, and it's now quite a vibrant community. There are a number of repositories now that use SBML. The biggest one is in Cambridge, England. It's got about over 600 models. It's funded by the European Bioinformatics Institute. It's a permanent resource. And these are all curated. So these are all published models. So if you find a publication and it happens to be on biomodels, you know you'll be able to get that model running again just by downloading it from that repository. So just to reiterate why such standards are important, at least in the systems biology community. One, it made it much easier to exchange models between different tools. And as I said, tools tend to come and go. So that's important. The other thing was that standard formats can be annotated. So we can add metadata to the models to make models more understandable. So for example, why did the author do this or do that? What assumptions did the author make? We can do things like that. And also if they use the symbol X, well, what on earth was X? Well, by annotating the model, we can figure out what X was. Once you annotate, you can also start decompose the model and put it back together in new ways. And so models become reusable. And of course, once they're also annotated, models become searchable. And this is used extensively, for example, in the biomodels database, where you can search for terms and it'll come up with the models that contain those terms. So although originally we had only we had small ambitions for the development of SBML, it actually grew and became much bigger than we anticipated. And now it's pretty much a standard format for pretty much all models in systems biology. So this is where I come then to the center of our Center of Reproducible Biomedical Modeling. So we want to continue this effort. One of the things that we discovered was it's not enough just to provide the model, because you also have to tell people, well, how was the model used to create the figures in the publication? And so this is one thing that the center is doing, is working on a new range of standards that will allow models to be, it'll allow researchers to know how was the model run, how was figure 5 created, how was figure 2 created, and so on, what kind of analyses were done. The other thing we're doing with the center is we're working with journals. So as I said, there's very little quality control at the journal end, and we're trying to work with journals to help them improve the quality control of published models. So we started a pilot with PLOS, in particular PLOS Computational Biology. So they send us models that are under review. We check that the models can be reproduced, then we send a report back to the journal and the editor decides what to do. So at least we now have a curation site that will check whether models are reproducible or not. And this relieves some work that the other reviewers can concentrate on the science, and we can focus on the model itself and whether it's packaged in a way that it can be reproduced by others. So what are the next steps? The US doesn't really have any significant repositories of models. As I said, the biggest repository is in Europe. The problem is, of course, sustaining model repositories. And I'll come back to this when I mention PubMed. We need technologies to manage published models. You can't just dump models on a site and hope people will be able to use them. We need some kind of archival standard. I'm just going to mention two things. Some archival standard we've developed, and the idea of a Docker type containerization. Those of you who are more computer savvy may have come across this thing called Docker. This is a way to package up a complete computer instance and to store that on the cloud. And if somebody wants to try out a model, they basically download this computer instance and run it on their machine. And it makes it very easy to reproduce work that's been done by other people. Okay, so in the next slide, I've just got a list of some of the main curated model repositories. We have Biomodels, which, as I said, is in Europe. It's got about 600 models. There's a site called BIG down in San Diego. These are what are called whole genome scale models. They've got about 100. These are pretty big models, also stored using SPML. And then JWS Online is another European venture that has also about 600 models in SPML with some simulation capabilities as well. So there are repositories. These are curated repositories. Models you download from these databases are guaranteed to reproduce what was in the publication. Okay, so let me talk about two technologies that we're pushing forward for the next stage. One is this idea of containerizing models inside what are called Combine archives. So a Combine archive is just a zip file. So those of you, I'm sure many of you are familiar with zip files. They're often used to compress data, and you can put lots of files into one file and then share them with your colleagues. But we've extended that idea, and so now we have a special zip file that lets you store all the information you need to represent a model. And this is the kind of thing that could be stored, for example, on PubMed. All right, so PubMed next to a published paper could have a Combine archive. And so this is just a zip file. And then the Combine archive could be downloaded by a tool that understands this archive, and it would unpack it and then run the simulation. So a number of groups are moving on this. Biomodels is going to be moving to using these Combine archives. We have many tools now support the Combine archives as well. Now, for those systems that don't use standards, you have a bit of a problem. And so for those, we recommend the use of this Docker technology, which is a way of taking your computing environment, your entire computing environment, and packaging it up into a single file. And there are a number of technologies for doing this, but probably the most well-known is Docker. This is mainly for packaging up Linux systems, but you can provide GUIs and so on to make it easy to use for newcomers. But this is probably a powerful way, and it's something we're pursuing in the center as well. This is a powerful way of packaging up models that can't use standards like SPML, but use raw code like Java, MATLAB, C, or whatever. This is an excellent way of packaging them up. And these can be downloaded by people and then run on their computer, and they can get the same results that were published. So these are two mechanisms that we're pursuing to help reproducibility. So almost done now. So the next slide talks about the role of PubMed. I think PubMed, being a library buff myself, I see libraries as a crucial place for storing, all of our knowledge, managing our knowledge as a society. And this includes academic libraries as well in the universities. My take on PubMed is that it could easily host the data on the models in archival form, either as Docker containers or as these Combine archives, or some other form that they find convenient. So rather than just store papers, they would also store alongside it the model on the data that was used, or at least a pointer to an official repository that holds that information. And I think PubMed could set an example for also the rest of the world and spearhead the move to the digital preservation of models. I was looking at the MCBK manifesto. I can see a direct overlap what we've been doing. I think there's a great opportunity here to have more conversations, and I'd love to talk more with the MCBK folk. I think there's something we could do here, actually. And I saw this slide from, I think it was one last year's talks, and this is why I realized, this is basically the vision we have as well. All right, so the idea is that I can go to a library, find a paper I'm interested in, of a model, and I can get the model there and then, download it and try it on my computer and see what the results look like and play with the results and so on. So I think we have a real shared vision here. So I'd like to talk more. So finally, because I'm so enamored by libraries, I got a couple of slides here just to show you. I wonder if any of you recognizes this. This is a Greek manuscript from the Vatican. You'll see a picture in the middle. I don't know if any of you recognize that. Maybe if I show you this second picture on the right, which should come up any minute now, this may give you a further clue as to what this manuscript is. Well, I'm just waiting for the image to come up. There it goes. So maybe some of you recognize that. Those of you who don't, I'll let you know. This is the oldest Greek manuscript of Euclid's Elements. So this is a 9th century copy. The original was written in about 300 BC. That's over 2,300. So for over 2,300 years, libraries were responsible for preserving such artifacts. Okay, the only reason we have this, and we have much of the Greek science still, is because libraries preserve that work. And I mean, the question is, work that we publish today, will that be available in 2,300 years? I mean, I think it should be. And I think the libraries are really the guardians of this knowledge. And I'd like to see them continue doing this and helping us preserve all the knowledge we have acquired over the last 2,000-3,000 years. So that's it. I just want to acknowledge NIBIB, of course, and Grace in particular, who's been a huge strength in this area. The NSF as well, and the NIGMS as well. Without these people, we wouldn't be where we are now. So great thanks to them. So if you have any questions, I don't have a clock in front of me, so I can't figure out whether I've gone over time or not. But if you've got any questions, please ask. Thank you very much.
Thanks to both of our panelists. This really was an extraordinary set of presentations. And now we have a very large number of questions. And I'm going to not be able to ask all of them. And I apologize to folks whose questions will not be addressed today. And again, we will try to scrape the questions that are not addressed and get some answers out to you. The first question is actually for Grace Peng. You mentioned virtual coach. Is there any virtual coach developed already, and how might it reduce medical error? This is from AJ Chen.
Thanks, AJ. So through the initiative solicitation that I mentioned, we are getting more and more people coming in with projects that are virtual coaches. The virtual coaches can come in any shape and form designed by the developers. We did not prescribe anything in particular, but the coaching really is to emulate what a real coach does, whether or not if we're talking about the music field or the athletic field. In the medical arena, the coaches are really an opportunity for the practitioner to be guided along, to let them know that you should watch out for certain things or certain things particular to a certain patient. Those things are being developed. And now with machine learning, people are now using a lot of the data from previously collected videos of surgeries to look at the errors that may be occurring because of the difficulty or the complexity of the surgery, to really systematically identify the differences between how errors can occur because of skills or the outcomes or the procedures. So the answer is yes, virtual coaches are being developed and more should be developed to further guide our procedures that are occurring every day. Thank you.
Thank you, Grace. And here's one for both of you. If models get too easy to just grab and reuse, how will risk of abuse be contained? Credibility is for each use, not universal. This is a question from John Rice.
That's a hard one to answer. I mean, the same was asked, when the atomic bomb was developed. If everybody gets the atomic bomb, aren't we going to have problems? Yeah, that's true. I mean, we hope that, people are responsible enough to use knowledge. Yeah, I'm not sure how to answer that.
I think an answer that I would provide is the 10 simple rules that I talked about in terms of credible practice really helps define the specs, so to speak, of your model and the context of use for the model. Of course, the question is about more dual use and use for not good, but in terms of the context of use, it helps us define the parameters in which the models can operate. But it also defines how the end user should operate the model. But in terms of responsible use of the models, I mean, I think that's the question that was being asked. It's a difficult problem, but I think responsible use of any kind of tool or technology we have will have the same issue.
Okay, thank you. Here's another question, probably addressable to both of you. How would phenotype repositories such as PHEKB and FEMA, that's PAEKB and PHEMA, fit into the kinds of standards you were talking about? This is from Siegfried Gold.
Hi, Siegfried. I think in terms of phenotypes, when I mentioned the lower back pain consortium, a lot of the data that are being collected right now are phenotypical data and almost anecdotal data and subjective data on how lower back pain occurs. And so phenotypical data is probably one of the most common data that are being collected. So it is really important to try to bring in that kind of data into the quantitative modeling process and the computable biomedical knowledge environment that MCBK is trying to promote.
Herbert, do you want to take a shot at that one?
Yeah, only to say that we have modeling projects and we model, detailed mechanistic models, but then we always try to relate those mechanisms to the phenotype that's of interest to the clinician. It sometimes is a difficult one to bridge, but I mean, I'm not involved in any of these phenotype databases, but we certainly have an eye on the phenotype that's relevant to the clinician. So.
Thank you. And I want to apologize to our audience. I am trying very hard not to use firearms expressions in this day and age, and I slipped, and I apologize for doing that. Next question is for Grace. For your digital twin, do you model via data elements and or behavioral functionality? How do you identify the components, and how do you know how well you were doing? This is from Ed Hammond.
Hi, Ed. Thanks for the question. So I think everything that you have listed would be involved. As I said, this is a sort of a dream concept that many agencies are now thinking about. The closest we've come right now, as presented by Medtronics and during the October meeting, which you can also see online in the IMAG Wiki archives, is actually a digital twin for diabetic patients, in which they have a digital twin of the insulin pump, as well as a digital twin of the pharmacological models being used by a particular patient. And the digital twin then informs the patient about their dosing of insulin and their pump and anything that needs to be done to upgrade or replace parts with the pump. And so if you think about all the components that are necessary to incorporate models for not only the devices, but also the physiology of the drug interactions, that's all part of the digital twin. And that is actually a very focused example Ideally, we'd like to have a digital twin of us in the healthy state, and then us with any sort of conditions that we might have, and in real time as we're growing old each day. So yes, we are interested in common data elements and minimal data sets. We're interested in defining standards for the sensors, but it is a very ambitious dream-like problem that we could approach as a community, and that's what we're trying to do.
Okay, thank you. This probably could go to both of our speakers. Now that we have standardized model formats, are there approaches to combine or have them work together to model higher order processes? The blue sky goal being to construct that digital twin. This is from David Jing.
Yeah, that's a great vision to have, actually. Yeah, with SPML SPML models can be combined to make higher level models. In fact, you can combine them with pharmacokinetic models as well. There are some areas that are still missing, in particular, multi-cell and organ-based models have not been standardized yet. But that is something we'd love to be able to do. As I said, once models are in a standard form and a particular annotator, you can start pulling them apart. And a number of people have done that with biomodels, for example. You can pull them apart and put them together in another way. And I'd love to be able to extend that to much higher levels of organization, multicellular organs, whole body. But we've got a bit to go yet. The main issue is, it takes a long time to develop these standards because you're dealing with people and people don't tend to like to change, and so you have to build the community and persuade people that this is good for the community, and it takes some years to make that happen. And my take on it has to be a bottom up rather than a top down affair, because if you get it from the bottom, it's more likely to stick around and people will generally use it. So yes, love to do it, but it might take another 20 years at this rate.
I guess I'll add a comment. Yeah, I'll add a comment. I didn't mention, but I'm also very much involved in the NIH Brain Initiative, in which we are looking at how the brain works from the top down as well as the bottom up. And when people try to reduce a higher order construct of how a brain process works to lower dimensions, that's generally what a lot of people are doing, is trying to reduce model orders in order to simplify understanding how the brain works. It's a very complex process. I guess I would tweak what Herbert said, that it's important to look at it from the bottom up as well as the top down, but in thinking about the systems biology point of view of the middle out as well. So, but yeah, I think any kind of tools that could help with moving up and down the scales of interest, spatial and temporal scales, as well as the different modalities and as well as species and different body parts, will be really important.
Thank you, Grace. Now here's a very MCBK question from Alan Flynn. What is required for open biomedical domain-specific model repositories, such as genomics repositories or cardiology repositories, to be sustainable? And how can the repository costs be recovered? Either one of you would probably address this.
Grace, do you want to start?
That's a really hard question. We struggle with that all the time in terms of maintaining repositories and making them sustainable. I'm approaching it from a government funding point of view. It's almost a philosophical question in terms of how long do taxpayers support a certain resource, and when do we transfer it over to a community self-sustained resource or a commercialized resource? When does translation occur? When does commercialization occur? These are all big issues. And I guess my answer is sort of depends on that repository, and it depends on that use, depends on how many people are using it and the need in the community. The COVID pandemic has brought up a lot of these kinds of examples where we've kind of thrown aside some of these constraints, so to speak, to try to address the pandemic as quickly as possible, to try to bring together multiple repositories of data and publications and models and trying to solve the problem. So I guess it really depends on the context of use and the issues at hand being addressed by these resources.
Thank you, Grace. Herbert, do you want to add to that?
Yeah, I mean, if you're talking about published artifacts like models and published data, I think PubMed is the place it should be. If it's published, PubMed is the ideal place, and they don't have to do much. They just have to store the material. We as a community can build the tools and so on, to work with that material, but at least there's somewhere where we know in 10, 20 years time, I can still get hold of that information from a published paper. So that would be a long-term, I mean, presumably PubMed will persist for a long time, okay? Hopefully for a few hundred years at least. And I mean, I would like to see PubMed take on the role of preserving these published artifacts. And then we wouldn't have to worry about having, long-term issues. So that's what I'd like to see.
Thank you very much, Herbert.
In fact, let me add to this. The European PubMed is already starting to do this.
Thank you.
Yeah.
These were excellent responses. We did not get to a couple of questions, and that has nothing to do with the quality of the questions, but rather the order in which I received them. We will try to get answers to the other questions to you all pretty soon. So this has just been a marvelous set of presentations. We're so grateful to our two speakers. We are now approaching a break in our program for about 10 minutes, and we will reconvene at 2:40. So thank you. 10-minute break. We reconvene at 2:40.